Okay, so welcome back, everybody, for the third part of the lecture series about toric symplectic manifolds. It's a great pleasure for me to introduce Felix Schlenk from the University of Neuchâtel. So welcome back. And he will be talking about like almost toric symplectic fibrations.
Right. So I get some echo, but it's very mild. Thank you very much, Ellen. And to all the organizers, I'm very glad to speak about this. So I speak about the, well, I did some stuff before on this, but I tried to arrange and to do it a bit more understandably. So the plan is, I have these two lectures, and the plan is to first say what toric fibrations are when you add the almost. So the toric we already got presented so nicely by Joey, and I want to get something less rigid. And this is a bit a strange thing because it appeared well by Hamilton some 15 years ago, but then it became extremely popular because Renato Viana used it to construct infinitely many different Lagrangian tori in CP2 and in other little bits of surfaces. And then very surprisingly, other results that had taken some, well, I've seen some interest by many people, were then proven much more efficiently. So I believe that these almost toric fibrations, it's a tool it's a setting one should learn, because if one thinks about something and for some reason it fits into this almost toric situation, then proof with some luck can just become much easier. So either you prove something new or you prove something old but 10 times shorter. So first I will say in a somewhat sketchy way, because the details are still not perfectly well written in the literature, I must say. People again and again write a bit, finding that what they can find in the literature is not good. And then what they write is again not complete. So, well, it's my opinion. And then to illustrate that this is a useful tool, I will give tomorrow and today one of them, today hopefully this application, and then tomorrow this and this application. So these are topics that people work on quite actively, and with these almost toric fibrations, one could do much, much more. So something like instead of one new object, infinitely many, or instead of one new space, a whole infinite class of spaces. So these three examples are just three examples I like a lot that illustrate how the almost adds so much to the understanding. Okay, so today I mostly speak about the how one goes from toric to almost toric, right? Okay, so I briefly repeat what toric was. So of course you can write down moment map and so on, but somewhat naively, and for most applications it's enough, it's just a symplectic manifold that fibers in such a way that on an open dense set you have good Lagrangian tori, and in the degenerate set where it doesn't quite work, you have isotropic subtori. So it's, well, if you have only Tn's, then it's boring. Then it's just some set in some open set in Rn cross Tn, or maybe not exactly cross, maybe with some monogamy. But this degeneration locus makes, of course, all the topology, as Joy has already illustrated, and the examples you must have in mind are Cn and Cpn, or to have the picture, C2 and Cp2. In a generic point here in the interior, so here, this is the positive quadrant, right? I mean, everything, R2 bigger or equal than 0. And it's not so nice here. I want it a bit thicker. Good. So in an interior point here, you have a full Lagrangian torus, and it's just, you can really think of it as a product torus. And at the boundary points, you have a circle, and in this only point, you have a point. Even easier would be to describe C, right? The picture would be this one, this point included, here till infinity. And what does it mean? It just means in the complex plane, this point would be this, and this would be the area encircled by the circle, and this circle would correspond to this point, and this circle to this point, and the origin will be this fixed point. And this here is just a product situation of the same thing. And for CPN, yeah, everything comes from this compactification. CPN, from this picture, you immediately see that CPN is a four-ball, namely if you take this line away, because that, when you look at what I just said here, you take only this part, is exactly an open four-ball when this line is excluded. And then you compactify, and over here, so let's just analyze together. What is over here? Yeah, by definition, here is a point, and here a circle, and here a circle, and here a circle, and here a point. So it's a sphere, right? It's a point and a circle and a circle and a circle and a point. So what you add is a sphere. So you already see that CP2 is somehow the four-ball, the open four-ball disjoint U in a sphere, and it is of course CP1 at infinity. So from this picture, you also immediately read off, for instance, CW, the composition of CPN and so on. One should not only think about these toric manifolds in terms of the moment polytope, but many, many things can be read off extremely clearly, like CW decomposition, cohomology ring, as said yesterday, and many other data, also in the complex geometry. Okay, good. That was what Shoei explained. And today, to fix ideas, I will only assume that the dimension is 4. My dimension will always be 4. Now it doesn't write, don't know why. Okay, so dimension is 4, and this is good enough. And there are developments that to do these things in high dimensions, but it's a bit tricky. But things are now going on since about for 1 year. But already when you would take products of such, CP2 and balls and C2s, you would get many, many new statements. So already by taking products, but for instance, to understand CP3 and the 6-ball, you would have to do something a bit more general, and it is a bit trickier. But today I want to restrict to dimension 4, the first non-trivial one. Okay, so now you know what such a toric vibration is. The good fibers are tori, and the other ones, they are singular. When you write down the moment map, then there are critical points there, but they have a very nice normal form. I didn't write it down, but it's not important because you know geometrically exactly what it means. You have certain families of subtori there over the singular strata. But now you want to generalize this, and you want to, but to understand this really, you should do something like Hamiltonian systems and look at Hamiltonians and their singular and their critical points and how bad they can be. And then you go into more theory and stratified things, and singularities are classified. And then what you would immediately do, you would in these lists see who is the best not so good singularity, and then who is worse. And of course, if you want to generalize, since it's anyway hard enough, you only take the next best one. And the next best one is the complex hyperbolic one. And at the singular point, you would have as a fiber a pinched torus. This really comes from dynamical systems. And of course, later in Lefschetz fibrations, and now people are much more in topology than in dynamics, people think of it completely topologically, but I think it's extremely nice to go forth and back between dynamics and topology in this business. So when you are a topologist, you would call the type of singularity that is added nodal, and if you are not, focus, if you are a dynamicist. In any case, it's a pinched torus. It's just the torus that has one vanishing cycle that is, well, this cycle here is pinched to it homologically disappears, and because it can be moved to a point. So such a thing has a local normal form, and for proofs this is quite important, but for understanding not. I briefly give it to you, more like for completeness. I never used it since I didn't prove anything about it. I only applied these things. So the local normal form, so what is it? You have a base, right? And then you have a point where over this point, it's two-dimensional, you have this torus. So in a little disk over this point, meaning in a four-dimensional set in the manifold M, you should find Darboux coordinates, meaning that the symplectic form is given by dx dy, such that the preimage pi of the projection of the origin is exactly this thing. And, well, up to now we didn't do much. And near, so in this neighborhood, the projection has exactly this form. x1, y1, you can read. So it's a stupid formula. But when you write it in complex coordinates, it becomes quite nice. It's a little bit strange because x and y are Lagrangianly paired. But if for a moment you forget about symplectic and think as a topologist, but more like as a complex topologist, but not for the complex structure compatible with omega, but for another one, namely saying that that the coordinate x is complex, x1 plus ix1, and y is also complex, namely y1 plus y1 plus iy2, then the projection is simply given by x bar y. So you write it out and you immediately find this not so nice expression. And this expression, I don't know exactly your background, unfortunately, but I kind of assume that you know maybe more topology than me and less Hamiltonian systems. So you may have seen that because this is what comes up in Lefschetz fibrations for symplectic manifolds all the time, right? This kind of singularity. But since I want to tell you something you may not know, I now will describe these singular fibers from a dynamical point of view. And I will not give complete proofs, but if you work on it, I think both points of view are important. And this was actually done probably, well, not before Lefschetz, but certainly before symplectic Lefschetz theory. So I give you an intuitive model that is extremely easy in Hamiltonian dynamics. It's about the easiest non-planar Hamiltonian system, just a spherical pendulum, right? So I have here such a rigid thing, and here I have a mass that I assume is 1, and the length of this stick is 1, 2. And then I have a gravitational force here, and of course I assume that gravitational constant is also 1. And then, so this bob here can move on an S2, but the configuration, the phase space is free, so the piece, the velocities can go anywhere. So the phase space is the cotangent bundle, and this sometimes doesn't write, don't know why. So this is very strange. Yeah, so it told me that he's writing, yeah. Anyway, you see here a T star S2. This is the phase space. And I just take coordinates Q and S2 that come from R3, and the P is 10 in these cotangent planes. And of course, you have the total energy E, right? And it's given by 1/2 V square, but here, because we are in cotangent bundle, is P square. And the norm is just the one induced from R3. The S2 is round. And then you have the Q3, the potential force that pulls downwards, and it's a plus. So this is one important function to understand the spherical pendulum. And then, of course, you look latestly after Noether, you look for other preserved quantities because you want to work on a smaller space. You want to reduce. And you, of course, you know that around the Z-axis, the Q3 axis, there is a rotational symmetry because the only force here is going along Q3. So you have this rotational symmetry, the S1 symmetry, and this must lead to a preserved quantity by Noether. And it is easy to understand that it's the angular momentum, right? Because you rotate, you turn. And the formula is Q1 P2 minus Q2 P1. I call this L. It's not Lagrangian, but somehow the momentum is called L. Okay, so now we have two good functions, and we collect them into one map, L and E. And so this is a function on T star S2 and takes values, there is a typo in R2, sorry, in R2. And Now you would like to understand what the image is and to understand the fibers of this map mu. I call it mu because it's really like a moment map, but it's also not quite a moment map because.
Could you go back to the previous page? I forgot.
Yes.
The information. L. Where is L here? Oh, L. Okay. Okay.
Fine.
Okay. I just want to remember what L was. Okay. Thank you.
Yeah, L is the angular momentum. You could write something like Q cross P projected to the R2, the 1, 2 plane.
Okay, thank you.
Something like this. Okay, so you have this map. And the first thing is, of course, to understand the image of this map. And this is actually difficult. So this curve is something like contains third powers and roots. It's strangely hard to solve. But anyway, it can be done. For instance, in this, there are books that write long formulas, but it's not extremely instructive. But, well, that it's something like a shield. By the way, it goes, of course, to infinity here, because energy, but I took only a part. But let's see who corresponds to what. So I claim that over such a boundary point, there is a circle S1. Down here, there is 1 point. In the interior, there is a 2 torus. And there is one very special point at the point 0, 1, at height 1. But here is height 0. Well, the height, when the energy is, how can the energy be negative? Yeah, when it hangs down, because there is a Q3, right? It can be, here is level -1. If so, okay, let's analyze. What is this point? Yeah, this is, of course, if the thing just hangs down and doesn't move, right? Then the energy is 0, and I have to subtract the Q3, which is 1. So I'm here at -1, and the momentum is also 0. So this point here corresponds if the bob with the mass is just hanging down, right? So what is such a circle? Yeah, I tell you, it's, you see, below the equator, you can indeed go along such a flat circle. Usually, most of the motions are something like this, and then from the other side, and so on. But when you are below this equator, you can really go like this. And this circle is such a circle. And when with the energy you go to infinity, you also have such a circle. And in the limit, it goes to the equator, but you cannot be higher. You cannot go along the equator. But epsilon below, you can indeed go along the equator. Need some analysis. It's, for instance, in Arnold's book, right? So these are these S1s, because they do not do any oscillation here. They kind of degenerate. These ones, yeah, they form whole T2s. Good. So a generic, you see, when I have something like this, then I already have this circle, but then I can also turn it. And then I got S1 cross S1. But if I have just this flat circle, I turn it, I get nothing new. Therefore, it degenerates to an S1. Of course, you also have this left-right symmetry. It corresponds to going around like this with the motion, or going around the other way, right? Something like this around. So when you want to understand everything over a shield, it's enough to understand 1/2. Okay. But now the most interesting part is, in fact, when L is 0. These are the planar motions. These are exactly the planar penduli. It means that the bob does not move around. It just swings. So it makes something like hop, 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 or maybe it makes, and this is, it maybe goes around, right? So the planar motions are exactly those, of course, that have L equal to 0, and they must correspond to points over this axis, right? And here are really the most interesting things. And what happens is, yeah, you already understood, with this pendulum, you can either make hop, 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 and this hop, hop is a circle. No, it's a torus, because you can do this hop, hop, and then choose the angle around this S1. And this would be a torus here or here. But then when you add a lot of energy, then the pendulum can go just around. It doesn't go uniformly around. It goes here faster, slower, faster, slower. So this is an S1, but you can turn it again. So you get up here, you also get a T2, right? But this T2 is quite different from this T2. This up here is such a motion, and this down here is such a motion, right? An oscillation motion. But now comes one obviously interesting locus, namely, and you in a way know that, it's when the bob stays like this. It's the unstable equilibrium. But who is at his energy, right? Who is at his energy and also has the same energy? Who is at energy 1 and also has no momentum? It's these somewhat theoretical motions. It's those that start up here at minus infinity and then in infinite time go around and at plus infinity come back. And all these are over this point because they have the same energy and they have 0 L. So these motions form the fiber over this point 1. So let's analyze this thing. I claim it's a pinch torus. Up here, already said, it goes around. Down here, it's like this. And what is here? I claim, I call it C for croissant. It is such a croissant, yeah. Okay, it's a pinch torus. Why? Yeah, because these ones, they are copies of R, right? You go at minus infinity, you start, and go and go and go and go, and the plus infinity come back. Then you have a S1 family of them. So you have like a cylinder. But at the end, this cylinder, well, it comes back and it actually gets compactified. It more looks, this cylinder more looks like this. But this point is the same as this point, and it's exactly this configuration where you stand straight up, the unstable equilibrium. So this compactified cylinder is exactly such a pinch torus, right? And this is the singular fiber over this point 0,1. And this was found by Hans Doistermatt in '84, long ago. Well, it was probably found before, but he analyzed monogamy too, which will be very important. Okay, I like this example because you can see so much in it of them, yeah, of many things, also Chern classes. Okay, so here in this system, we have found just one new fiber, and everything else was like in Joy's talk, but one thing is new. Okay, one new fiber. Questions? Great. Okay, so now I want to discuss that. So you see, when I take out this fiber here, this special fiber, you know, I have something very similar as what Joy did. Let's take out also the S1s at the boundary and the fixed point. Let's take the interior of the yellow shield and also take out this special pinch torus. So what is it? Yeah, locally, this is by Arnold Liouville or even by Liouville, in fact. Locally, this is like a disk cross T2. But globally, it's not trivial. And this is very easy to see. Because, so I claim that this vibration, if I take the interior, is non-trivial T2 vibration. And the reason is simply you analyze, right? If it were, so the idea is, if it were trivial, then this level set here above the special fiber should be diffeomorphic, one can argue by flow arguments, but let's say homomorphic, enough for us, to everything over this level. Because yeah, if this vibration is trivial, well, it's equivalent to say that it's trivial over this curve gamma here. And then when it's trivial here, then you can easily move this down to this level to create at least a homotope equivalence, just like in Morse theory. You go a bit above the level and a bit below. But these two levels, this one and this one, are different. Because what is the level here? Yeah, it's the same as here. This is easily seen to be a Morse non-degenerate, a Morse minimum. So therefore, this level here must be an S3. Yeah, just like everything near a non-degenerate minimum. But this level here is, of course, yeah, what happens when you look at the geodesic flow over S2, right? It means that all the energies are the same. So you can go to tangent or cotangent vectors. They all have the same length. This is exactly the configuration space of geodesic flow. So this is T1 S2, which is, of course, RP3, which is different from S3. So it means this vibration is non-trivial. There is monogamy. This was only detected in '84 because dynamicists were not fit for topology, and topology is not interested in dynamics. But then some people start to join this. I started with Smale, and then Doistermaat, and then many other people, Moser. Okay, so for us, this is not quite good enough to know that it's non-trivial. We really have to compute the monogamy. So I will not fully do it, but I will describe how it can be done. So there is this non-trivial monogamy, and I want to say what it is. So, okay, I have to choose a basis, and there are canonical bases. So let's take the torus, the pinched one, and I take the obvious, well, I take the, so we have to compute monogamy, right? To compute monogamy, well, these toruses are a priori not in the business. I take a torus here, a torus here, a torus here, a torus here, and I go around and I look how a basis chosen here, this is my point gamma of 0, will come back. But the choice of basis is governed by the pinched one. So I choose on the pinched torus, I choose really a basis of the homology, the eta curve. It's just like in S1. And then I also choose this one, namely the vanishing cycle, the only the only interesting curve that can be moved into the pinch point. Okay. And then when I go to a nearby torus, of course, this gives me a choice of basis. So imagine this really very nearby. Then I choose a basis, such a nearby curve at 0. Again, I cannot write. And a nearby curve lambda 0. And this I do on every nearby torus. And now I can compute monogamy. And I will not do it. It takes a full lecture. There are many texts again, because everybody thinks he has to do it a bit better, either more intuitive or more computational. I like the text by Heckmann very much. So it's only about 3 pages. But the outcome is that the lambda 0 curve, the blue one, is just mapped back to itself. But the eta curve gets a shear contribution. You have to subtract from it once lambda 0. So the monogamy matrix in the basis eta lambda is the one written. And this, of course, is exactly the Picard-Lefschetz formula. If you think about this pinch torus in topological way. But yeah, this is also not so easy to present. I think it takes some time. Of course, it's on page 1 of Arnold Gosensade and Parchenko. Yeah. Okay, good. I just give you this as a fact, and you may have seen it at the Lefschetz side. Fine. Okay, so now I want to introduce a notation. So notation is for this normal form around such a almost toric vibration with such a pinch torus. And this is my notation, and it can be a little bit confusing. So this is really a notation. And what does it mean? It means the following. At the cross, there is the singular pinched torus, the croissant, the focus-focus singularity. The dotted line only remembers us that if we go around, we have the monogamy that we discussed. Just this. It's only to remember. And it's also useful to understand something else. So what do we have over this blue boundary? We have not an S1 almost here and here and here and here a point, but we have everywhere S1s. And the union of the two blue segments, the preimage of it, is actually nothing singular. It's a smooth, straight cylinder. Because the corner is an illusion. This corner here, by the monogamy, is actually in reality straightened up. The monogamy, this -1, is exactly such that in reality, this is a straight cylinder. Okay? And what I mean with this is just so, okay, this straight cylinder, and then at every other point at T2, and there is monogamy about the pinched torus, this normal form, singular Lefschetz fiber, and this picture is an abbreviation for it. And this is a locally a topology. Yeah, it's a smooth manifold in some way. Okay, and we will prove it's a symplectic ball. This is very important. Okay. So, of course, from Joë's talk, you also know that this one is an open four-ball of size this length, right? Because this is a part of C2 of R4, namely all those whose radius square is less than or equal than this. And this is excluded. So this is an open four-ball. And I claim that these two spaces are symplectomorphic. So I didn't very well discuss, I guess, the symplectic structure here. Over good points here, it's the usual one. Over here, it's also what you think, because, you know, this is just a copy of what again? Of S1 cross, no, of T2 cross R2. So it's clear what I mean here. And here I just mean this monogamy thing. But you see, it's symplectic. Then when I do this monogamy, it's GL2Z. It's actually clear what I mean with the symplectic structure here. And I claim that these two models are both the same open symplectic ball of this length as pi r squared. Okay, so this was first written by Symington, and she writes very short. And then other people, like in the notes by Johnny Evans, they write something else. And I believe nobody is totally complete. But now I just take the point of view that you know a bit more topology than me, and I repeat you Symington's proof, and probably it speaks you somehow. I think for you it will be kind of okay. I also believe it, but I'm not good at that. But I want to tell you how that goes. So, okay. First, so I must understand what this is, and then this croissant. First, I only take the preimage under this projection of a little disk containing the singular croissant. And it is known that this, so, okay, there are two steps. First, I prove it's a smooth four-ball. And then I claim it's symplectomorphic to the usual one. Okay, two steps. First, a smooth structure. So you probably know from Lefschetz theory, and this indeed can be learned in the book by Gompf and Stipschitz. It is this little disk cross T2, and then you want to make up for the singularity. And what you have to do is you have to attach a two-handle along a simple closed curve, they say at the boundary of the disk. This I don't understand, Ceylon. Why should it be on the boundary? It could be anywhere, you know? Does it really have to be on the boundary? They say at a point at the boundary of the disk. Cannot change anything, no? When you attach it at the interior torus somewhere. Well, I don't know. So this you learn from the Lefschetz people. that this here, the fibration over here, is T2 cross a disk and a certain two-handle attachment, and you have to give the framing. Okay. So now I want to say what happens if I add, you see, I mean, whether I take this or the interior here is of course the same smoothly, but now I want to add this. But remember, it really looks like this. So when I would restrict here, the difference between this open and this closed is exactly the difference between cylinder and disk, because you collapse here one circle. So now, since I add all this line here, it means that this here is changed by this T2 cross B2 becomes an S1 cross B3. Think here of S1 cross interval. One S1 becomes an interval if you add here this cylinder, because you compactify. It's like the transition from punctured disk to disk, right? Okay. So the space we want to understand is this thing, S1 cross B3 with a two-handle attached. But now, of course, we write the S1 cross the 3 ball as 4 ball with a one-handle attached. This I also understand. And then we rewrite this identity, and we get that what we want to understand is a 4 ball with a one-handle attached with a two-handle attached. Yeah, but I also read Milner's great H-cobordism book. The one handle and the two handle, they cancel. They are in cancellation position if you think of Morse functions, and therefore the whole thing is just a B4. Okay, I think this is not a proof, but this is what specialists probably can make really convincing. Probably most of you. So now to see that this is symplectomorphic to the standard ball, I believe in the literature this was not done. So it goes like this. You see, when you have this picture, you can put this single fiber either here or either here. That nothing changes if you go more in. This is an easy Moser homotopy argument. But at the very beginning, what happens symplectically, I cannot understand easily. But with high tech, I can kill this problem, because you see over here, everything is standard, and over here too. So what we now have is here the standard symplectic ball, and here we proved it's a ball with some symplectic form that here near the boundary is standard. A deep theorem using holomorphic curves. It is written up by McDuff, but we call it the Eliashberg-Fleur-McDuff theorem. Says that such a manifold is globally standard. If you on the round smooth ball have a symplectic form that near the boundary is the usual one, then there is a symplectomorphism fixing a neighborhood of the boundary that maps the difficult form to the usual form. This uses foliations by holomorphic curves. And it's not easy, but at least this theorem tells me that this is really all true. But probably it's also, Margaret Simon does something elementary, but I could not quite understand in the very beginning. But later then, when you move over, then it's indeed the standard Moser isotopy argument. Okay, good. So this is now for the sequel very important.
Different from Moser's theorem.
Pardon?
How is this different from the Moser's theorem?
Yeah, so Moser theorem says that if you have a symplectic form, if you have an isotopy of symplectic forms, let's say on a closed manifold or on an open manifold that agree near the boundary, that all define the same cohomology class, then you can find an isotopy of the space that deforms the first form that induces this deformation by pullback on the forms. But the problem is that from this argument, I do not know a priori that my two symplectic forms are isotopic. You see? This is a deep theorem to say that the space of symplectic forms on a four-ball that are standard near the boundary is connected. This statement is very close to the McDuff-Rierschberg theorem. It's probably equivalent. But such statements are the understanding of the space of symplectic forms on a given manifold is extremely hard and essentially only solved for surfaces and the four-ball and CP2 and S2 cross S2 and nothing else. It's totally open for CP3. It's very strange. In symplectic topology, you can ask many questions and some are approachable and some not. And sometimes JDIS gives something, but hard problem. Good. But for the sequel, for me, it's now crucial for all the rest that this picture that of course represents the usual toric structure of CP2 can be reinterpreted in this way. And this looks like a totally crazy move. We replace an easy fibration by a much more difficult one, but the benefit will be enormous. This is very strange. You go from the perfect picture to the lousy picture and will profit from it. Fine. Okay, now we are here. So we understand that CP2 is also now this. This is now an almost toric fibration of CP2. Here at infinity, I didn't do anything. And now so this is what we discussed. And now this point I can move, and this is simply a Moser argument. These symplectic forms are isotopic, and since cohomologically nothing happens because I don't touch infinity, they are cohomologous. And then it's a very easy Moser argument that says that away from a little neighborhood, the forms are the same, and there is an isotopy moving this form to this form. But now comes yes.
The normal bundle, the 1, 1, 1 on the edges of the triangle. What is that? What do they represent?
The 1, 1, 1, the length, or if you want, the symplectic area of the sphere. That is the preimage of this segment. There are sizes. I will use sizes a bit later, but I already start now. These ones are sizes. Symplectic sizes, if you want length or symplectic sizes. Here it's the Euclidean length, but here it's not the Euclidean length, it's the affine integral length. In all this business, you always work with affine integral length. You know what it is? When you have the set, oh, my thing doesn't work. I say it when the pen comes back.
What did Vienna do exactly? I mean,
Vienna invented this move, the C.
Repeat that moving.
It's a coordinate change. C stands for coordinate change. It is a trivial insight that is totally ingenious and key for all the applications. You just redescribe this almost toric vibration on the right down by the following. This is called so first you do this is called nodal slide. This is really a bit boring that it doesn't come. It doesn't come. From the picture right up to the picture right down, you just do Moser and bring the cross near the boundary. But shortly before the boundary, you stop. And now you do just a coordinate change. You describe exactly the same thing, slightly different. Namely, you undo the monogamy. You don't say that you have monogamy over this dotted line down right, but over the short dotted line down left. And when you want to do that, you have to compensate, namely the transpose inverse of the monogamy map, you should apply to half of the two. You can choose. I chose the green triangle on the right. I must apply the transpose inverse of the monogamy map, and I get the new green longer triangle. So instead of writing the down right triangle, you can look at the left down triangle, and it is another way to describe CP2 in an almost toric fibration way, and the length is changed. There is now a 2, a 1/2, and a 1/2, right? And almost nothing happens. You saying that the monogamy along the longer dotted line, you give it up, but then you must do something in the fibers, namely the transposed inverse. But when you do it where you had no monogamy, now you must say you have, because you changed the fiber. You see, the point is that if you have a 2x2 matrix A, then A cross A transpose inverse is symplectic. Do you eat this? Sorry, I cannot write. Oh, now I can. Do you see, this is resolved at the expense of shearing this down. And this monogamy now disappeared. Okay. And it is for all the sequel important to work with this triangle and not with this one. It's called transferring the cut. You transfer the cut here, no, the cut here to the other side, but then you get a thinner, longer triangle. Okay? Great. So now we are essentially almost fit for applications. So I now need, I don't want to work with this length. When you go to foregons, it will be key. With triangles you could, but it's not nice. It's much nicer to look at integral weights. What is this now? It's much nicer to work with integral length over at the vertices. For triangles, it's equivalent. When I give you the integral weights at the edge, at the vertices, you can up to scale reconstruct the triangle. So it goes like this. I take Q1, Q2, Q3. They are vectors with rational slope of integral length 1. I briefly say what integral length is. You take the Z cross Z lattice. This is integral length 1. This is 1. This is, oh, I forgot. This is 1. You see, you take a rational vector, any, a rational segment. Then you translate it so that it starts in the origin. And then you look how often you cross a lattice point. And this is its integral length. A better definition is you choose a matrix in GL2Z, transform this guy to an axis, and then take the Euclidean length. This is the integral length. Okay? So what we do is we take I take here a vertex, and then I take, for instance, for W1, I define it, I take Q2 cross Q3, it's the determinant, and then just the absolute value of the determinant. So the absolute value. This is the integral weight. And they encode the basis up to scaling. But you know, the RA is anyway always fixed because we always operate on half of it by GL2Z. And so I start in the beginning with size 1/2 or size 9/2, depending how you scale. So these integral weights are perfect. So instead of thinking of this triangle, I think of this. It's clear that here are ones, and the 1 minute computation tells you that here the new weight is 4. And 4 is 2 to the 2, and this will be very important. Okay, so from now on, the triangles I create in this way, I encode by these integral weights. Good. So now, instead of starting with this CP2 triangle, I prepare it and I pinch it at every vertex. because by Hamiltonian theorem, I can do it. You know, this one we discussed, and the other angles are, of course, the same. They are SL2Z equivalent, and CP2 has this huge symmetry, right? It's clear that every vertex looks the same. So I already prepare it, and I take here these slides. And now we already did one slide. I made hop. No, doesn't work anymore. Duck and down, and then go parallel to it, and then we got this triangle. And once I have it, well, I get now here a little slit. This guy comes down, and then I can again do and do and do. I created here a new fresh thing, and I can go in, and you can try to iterate. Okay, again and again and again, and you get many, many triangles, and each of them will be very useful. So I want to describe them. And that's what Viana did, and also Michalkin and Usnich and Galkin and other people. So I first will just give you the answer, and then we see a bit how it goes. So the really fantastic, many things in this numerological symplectic business is observation dependent. If you observe something, you have a great paper, and if you don't observe it, you're slightly later disappointed because somebody else did it. Yeah, happens all the time. So you should, I should have seen it, I must say, but okay, stupidity is just, it's how it goes. So you take the Markov equation. It's the famous equation for natural numbers, positive integers. A squared plus b squared plus c squared is 3abc. It's a certain, it's order 2, order 3. It's a bit strange, but it comes up in many branches of algebraic geometry and number theory. And Markov, 150 years ago, proved, not quite, he classified the solutions. So the very elementary thing, but again, you have to observe it, is that if, of course, 1, 1, 1 is a solution, right? Markov's observation was that if you have a solution, you do a so-called Markov move. And the Markov moved triple is again a solution. It's a two-line computation. You just insert. Much more important, these are all solutions. There is nothing else. Every solution is obtained in this way. Of course, you see, you can choose. Here, I have taken C, and I have Markov moved C to 3 times the other 2 minus C. I could have applied that to B. So what happens is that you start with 1, 1, 1. Now, since they are all ones, in the first step, maybe you cannot see that. Hopefully you can make this a bit bigger. Maybe I can make it a bit bigger. In the first one, you don't get new things, only one new, but not many new, 1, 1, 2, because you have so many 1. And then here, when you apply here, the Markov move to 1, you get 1, 2, 4. If you apply to the one you just created, you bounce back. You get then what you already had, right? You see, when you create 1, the 2 now by this move, and then you take C equal to 2, you just go back. Now, when you are here, when you apply to 5, you go back because you just created the 5. But then when you apply to 1, you get 2, 5, 29. And if you apply to 2, you get 1, 5, 13. And then once all the numbers are different, you get a trivalent tree. Not hard.
I'm confused. If you do 1, 1, 2, that move, you'll get 1, 1, 5, not 1, 2, 5. Because you're not moving the first.
You're here.
Yeah.
You
So
take like B to be 2 and C to be 1, I think.
Yeah, maybe I say it wrong. So if you take either of the ones, you get this, and if you change 2, you go back.
No, I mean, when you apply this move, you don't move 2 coordinates, right? AB stays the same. So if AB is 1, 1, that's
no, I reordered a little bit. You see, I took 1, 1, 2. I choose, for instance, this one. What do I get? I get 5, 1, 2. But then I always reorder.
I see. Okay.
Okay. No, good point. One can get very confused, really. I mean, I always get confused. So the convention is just that you reorder here. Okay, so you get this Markov tree. And in the rest of my lectures, I don't know what's the time, yeah, not so much. So I will prove that for every such triple, you get a new Lagrangian, monotone Lagrangian torus in CP2 and in B4. I will also prove that for each of these nodes, you get a non-isotopic symplectic embedding of a cube into a ball. And today I will start proving that if you look only at the upper branch, you can prove about a third of the symplectic embedding problem ellipsoid into ball in, well, half a page and not 30, as it happened to me with Tusa McDuff. Okay. So, okay, so these toric, almost toric fibrations that are encoded by these Markov trees, they are now, from these come all our applications. Fine. Okay, so, yeah, of course, we should verify that if you do, right, these operations, the first one we did verify together. Again, it doesn't work. Well, so, oh, now I'm a bit afraid. So we already constructed the 1, 1, 2 square by, it's called mutation, slide plus this shearing back coordinate change of Vienna, it's called mutation. If you apply this to the usual triangle, the toric fibration, you get the triangle 1, 1, 2 squared. But what happens is when you go on with these mutations, you get exactly this tree. You see the 1, 1, 2 squared is this guy. If I now would treat it, I would get the 1, 4, 25. These are the weights in the corners. They are the squares of these Markov numbers. And this was observed independently by Galkin and Usnich and Galkin Michalkin before Vienna, but then Vienna, okay, did it, wrote faster and did it also a bit differently. Michalkin and Galkin used toric degenerations, more like from algebraic geometry, and Vienna did it a bit more symplectically. And now, okay, so once you observe it, that the nodal slide transforms the ABC triangle in something, then you compute this something and you immediately check that it is the Markov move. So these, you like exercises, here it is. It is not so difficult, but it is not 10 minutes. I think you can do it in half an hour if you want. Would be not very instructive to write it down. But once you observe it, it's an exercise. Okay? So this mutation, this shearing around, starting from the CP2 triangle, corresponds exactly to the Markov tree. Fine. Okay, now I start the first application. Do I have 10 minutes or not?
Actually, it's almost time, but of course you can go 5 to 10 minutes.
Okay, maybe I take 10, otherwise I will say nothing. Okay, so I wish to explain you why this solves half of the symplectic embedding problem, an ellipsoid into a ball. You may be not interested in this, but I like that very much. And questions when a symplectic domain embeds into another symplectic domain, let's say in dimension 4, in a way is a nice business because it leads to many surprising phenomena and connections to question number theory. And also it gives you an impression what symplectic means, because symplectic is somewhat non-intuitive in contrast to Riemannian. And here you get a feeling what symplectic rigidity and flexibility means. Now I started with Krylov on squeezing, and now we ask a final question. We take an ellipsoid. It's just what you think. This is the ellipsoid if here I would have written B. But you can always scale things by one scale factor. So I assume that B is 1 and A is at least 1. without loss of generality. And the moment map, the moment polytope under the usual moment map is just this triangle of size 1a, right? 1 is fixed and a is a parameter. And the business is now to ask, what is the smallest ball such that this ellipsoid symplectically embeds into the ball? And the answer is called the capacity, the ball capacity of A. If A is 1, the answer is 1. And if A is bigger than 1, it's not clear. Okay? But what is clear is that there is a volume constraint. Namely, of course, if this ellipsoid symplectically embeds into a ball, the volume must be less. The volume here is A times 1 over 2, and the volume here is A squared over 2. So it means that certainly you need at least root A for the ball capacity, right? So then now we have a graph. Here is 1 and here is root A, and we search a function, and it must be a monotone thing here. And at A, it's the size, it's called C of A, the smallest ball size, so that the ellipsoid 1A symplectically embeds. But this A is not the radius, it's pi radius square, because only surfaces, areas make sense in symplectic, not radii. Okay? And this function is known. I worked it out with McDuff some time ago, and it has 3 parts. Until golden ratio to the 4, there is an infinite staircase that I will come back to, until tau to the 4. Then there is a zone of transition with 7 steps, and then the answer is simply the volume constraint. So for a bit more than 8, you can fully fill, and then between 7 and this number, or maybe a bit more than 7. Tau to the 4 is yeah, okay. It's around 7. It's 6.85. Okay, there are 3, right? The transition phase between flexibility and rigidity, then the total flexibility you can fully fill, and here something like structured rigidity. And this I want to describe. This is the most interesting part. The answer between 1 and tau to the 4. Okay, and it looks like this. So when you draw it realistically, it is not so spectacular because you don't see much, but in reality, there are infinitely many steps, and they are all extremely structured. So the first step is here, of course, 1, at 1 it's 1, and at 4, yeah, it's 2, and we actually already saw that, but I must relate it. And then there are always such steps. So this is a line through the origin, and this is also a line through the origin, a segment that extends to the origin. And this is just horizontal. So to describe this infinite staircase, I only have to tell you the numbers where you touch. I only have to describe you one step as a function of n. It's a sequence of such steps. I have to say where it starts, where it ends, and where it breaks, right? Okay, let me describe such a step. This is done by Fibonacci numbers, strangely. So you take, as usually, Fibonacci numbers with recurrence, and then you take only the odd index guys, only each second. They are 1, 1, 2, 5, 13, 34, 89, and so on. And then you take the quotient of consecutive ones. So you get these numbers. And this sequence converges to tau to the 2. And then you can already describe everything. You also, now I must say, I can tell you what is A. So I describe now one step, namely the nth step. The height at AN, which is this quotient to the 2, is, the root of it, because it's on the volume. This is just AN plus 1. And up here, things are now also determined, because gamma n plus 1 is also given by, well, gamma n is this quotient. And the height you can now compute. It's the difference of not neighboring 1, but distance 2. So the Fibonacci numbers and their quotients and squares describe the n step, and the whole answer is made from these steps. Okay? This is just information for now. Good. For this symplectic embedding problem. So now there is a little lemma, and I will not go through the proof because to understand it's very easy, but it takes 4 minutes because one has to say something. So the interesting thing is, it's enough to prove this to prove this step. It's enough to show that at AN I can give a full embedding, and at BN I do have an obstruction that strong. You don't need to prove that at Bn the answer is gamma n plus 1. You only have to show more or equal because the graph is monotone. Of course, it cannot come down. It's also easy to see it's continuous. I only have to, it's very easy to see that to establish the n step, it's enough to see that at An, it's at most gamma n, meaning that you can fully fill, and at Bn, it's at least gamma n plus 1. And I leave maybe for tomorrow the proof to you. It's very easy. It's about scaling and a certain quotient and some little trick by expanding. Okay. So now I do not prove you the blue inequality. It has to do with blowing up, going to decompose. You have to decompose ellipsoids into balls. Then you have to do multiple blow-ups of CB2. And then you have to find the correct obstructions coming from holomorphic spheres in blow-ups. So this is a bit along the line of Gromov. You search the right obstructions and you use that embedding balls is the same as doing symplectic blow-up and finding certain proving that certain cohomology classes on multiple blow-ups of CP2 are representable by symplectic force. This is a bit a long story, and it's different from what I want to do here about almost toric fibrations. So the blue thing, I've written surveys, and you can read it in McDuff's papers. And so the blue one I don't want to show, but the red one I will completely show now. Well, not now, maybe tomorrow, but in these 2 lectures. Okay, the blue one. So for the blue one, we must find for the ellipsoid of size 1 AN, we must take the ball of size, well, the same volume, and maybe add an epsilon root AN, and then we must be able to find a symplectic embedding. So it looks incredibly difficult. So this I proved on more than 30 pages with McDuff. What we did is we showed that there are no obstructions from J-curves and used a theory telling that all the obstructions do come from J-curves. And we used computer codes because it was just too much. But now, with these almost toric fibrations, these embeddings are not only obvious, but also explicit. Because from the previous method, nothing was explicit. It was totally non-explicit. So I will now try to, okay, I should probably stop, but okay. So this I don't want to do, but I want to stress, and this I will probably start tomorrow, that you could do it without almost toric fibration. But in addition to all this blow up and symplectic business and J-curves, you use in addition to other things, namely existence theory for J-curves from Seiler-Witten, plus symplectic inflation. That is a beautiful thing, but again, a symplectic construction that is pretty tricky. Once you learn it, okay. But from so what will happen is that these Markov triangles that have one of the entries equal to 1 are exactly bases that are accommodating an ellipsoid. And that's it. Because this is a CP2 in some way, and I will just put my ellipsoid here, and these stupid, ugly crosses here, they I can make them as short as I want. So I have them away from this epsilon region. Here I have my 1, and I will just have here my ellipsoid. And that will do the job. So I will briefly verify, starting next time, that these Markov numbers are indeed related exactly the right way to the Fibonacci numbers. And it happens because when you put a equal to 1, the Markov equation becomes a squared plus b squared plus 1 equals, no, I don't have to write the Markov equation. I have to write the Markov move. C goes to 3ab minus c, because b was 1. Okay, I take b equal to 1. And you know, these odd Fibonacci numbers have exactly this recurrence. Between Gn and Gn plus 1, you have exactly the Gn plus 1 is, Gn plus 2 is given by 3 Gn plus 1 minus Gn. This just comes from the Fn Fibonacci recurrence when you go step 2. So since they have the same recurrence, the Markov move business will exactly correspond to these Fibonacci numbers. And that will make that we get exactly the triangles we want. Okay, I will do that in 10 minutes tomorrow. And then tomorrow I will at least explain why there are infinitely many Lagrangian tori, that they are non-diffeomorphic, non-isotopic, and then maybe the cubes I cannot do. Now we'll see. We'll see. I can give you another survey if you're interested in cubes. Okay, I blah blah enough.
That was great. Let's thanks to speaker. And any questions?
Well, I must admit, I missed the main point of your lecture, not because you didn't explain, because I have such a thick brain. You were explaining toric fibration, good.
I'm sure I didn't say it.
Then you were explaining this trick, Vienna trick. I was trying to understand what this trick exactly, in terms of handle, because I can understand handle what is of toric fibration. While I was thinking that all of a sudden, I realized we are talking about some numerology, Markov numerology. You jump to Markov numerology, then I was totally confused. So it's most of my,
very good, very good. So the first thing I try to kind of say is why you can strangely not look at the usual vibration of CB2, but another one. That was the first 40 minutes. That was just to say we can write down a strange, almost toric vibration of CB2.
I mean, even going from top left to top right, what did you do? There's an arrow, you did something. So
no. This is the key step. There is not an arrow, but a symplectomorphism. This is the symplectomorphism of Hamiltonian.
So what's the picture on the right?
This one.
Yeah.
This is the first, not toric, but almost toric vibration of CB2.
It's when there's a nodal point, nodal T2.
There's one nodal point, and there is monodromy around it. But I proved that this picture, well, I kind of sketched, but here open is exactly the usual ball. So if I add the line at infinity, I also get CP2. The symplectomorphism is the identity over here.
Shouldn't we have the tubular neighborhood of that nodal thing, a cusp, something like a cusp or a fishtail or something? I mean, it seems to be attaching a handle to maybe fishtail or a cusp to getting a ball.
It is literally S1 plus B3, what he said, right?
No, about fishtails, I know very little. So you don't believe that that this thing is a smooth ball?
No, I believe everything you said. It's just I don't understand because I'm new to this thing. While we are talking, I'm trying to construct this handle body picture, but I'm failing it badly. Somehow you had a S1 cross B3 and not a fishtail, but some kind of two. I mean, you are attaching two handle. Attaching circle could be complicated. You can still get a four ball. You are doing something like that, right? I mean, yes.
Yeah. So first you argue from. Would be good if it wrote. First, you argue that the restriction of the vibration over the little disk neighborhood of this cross here,
yes,
is T2 cross the little disk and the two handle attached along a simple closed curve over a two torus in T2 cross D2. What they wrote is at the boundary of.
You know what T2 cross D2 is? So you're claiming by attaching a single two handle to that, you can get
T2 cross D2 disk.
Yeah, T2 cross D2.
Yeah.
How can you get a four ball by attaching?
No. This was true for, unfortunately, it doesn't write. This was true for a little disk around the preimage of the vibration of a little disk around the cross. But then you see here the cylinder here.
Yes.
The cylinder over the blue two lines is now also attached. So now this is where I am. This is now something else. So first you start with the preimage over this, here it is, over just this little neighborhood of the special point. And then I claim from Lefschetz theory that this is T2 cross a two disk and a two handle attached.
It's -1 framing. That's a fishtail.
Okay, so this is fine.
Then somehow you will inflate it to ball.
Yeah, but this is not all. So this is what I say is a little neighborhood over the cross. But what I want to describe is this thing together, and then here there is a compactification, right? So
when you draw two vertical line segments, those are CP1s. Right?
No. This union is a cylinder.
Oh, okay.
The union of, because there is monogamy, it's like this, and over each point in S1. Okay. So it's like this. This open is S1 cross an interval, but this closed is a disk, right? Because you add in the annulus the central point. So when you add this cylinder to this business, the T2 cross B2 becomes an S1 cross 3 ball.
Okay, I can do that. I can figure that out. Okay.
Yeah, it's somehow this picture when you the moment map. If I have what is the half plane is the best. So when you take this half plane, and we speak of the usual moment map, pi norm square of the first complex coordinate, comma pi norm square of the second. If I omit this line, then this is T2 cross R2. But if I add this line, then this is S1 cross R3, right? Because once these cylinders, these open cylinders become disks. right? This open is the moment map of C star, but this is the moment map of C, the moment polytope of C. So when you think of this corner just as a line, you see that ignoring the attachment part, then one of the circles becomes filled in. So instead of S1 cross S1 cross interval, we get S1 cross interval cross interval cross interval. So we get this.
Okay, I guess I can think about this.
Yeah.
Too much time.
Okay, yeah. So Simon says even less. Maybe less is better.
But then at this point, okay, there's some construction, we can figure this out. Then there's some numerology, Markov.
Yeah.
How did you generate Markov from here?
Yeah, this was just a topological thing. But now we put in sizes. Sizes are very important because I have monotone Lagrangian torus already. The starting guy, well, it's not any torus. It's the monotone guy, the Clifford torus. And then, these come up only tomorrow, but these triangles have sizes, integral sizes. And this, when I think of after this move, this mutation, this is called mutation, nodal slide plus transferring the cut. Thinking like this is not good for the sequel. I must do this coordinate change. And then I have, as close as I like, near one corner, I have this strange pinch torus. In the middle, I still have a monotone torus. It's the same one as here. It will be exactly at the same position. And it was here at 1/3, here at 1/3. And this left part I shear down, and I view my CP2 now almost torically fibered like here. And here are sizes. First, they are length, but it's much better to think about angles. The angles are 1, 1, here, sorry, 4. And these integral angles determine this triangle up to scale. But scale is not important because the area is an invariant, so I can always rescale immediately if I need. What we will see in the next two applications is that the triple given by the integral weights completely, if two tori, for instance, this torus and this torus want to be symplectically the same, or even, let's say, Hamiltonian isotopic, then the triple of integral weights must be identical. They are complete invariants of these tori. Therefore, I introduce these numbers now.
I see.
For the ellipsoid, it was also important. For instance, this embedding of E1, 4 into a four ball of size 2 plus epsilon. It was constructed 20 years ago by some different technique by Obstein, and it was a little sensation. But here it's trivial because this triangle, when you slightly rewrite it, so what is it? Here it is 2. This is integral angle 1, so I can write also a vertical angle. And then I have here 1/2 and the other one, and here it's 1. So up to a scale of times 2, it's this. And where does it sit? It sits in CP2 of size 1. So this guy embeds into B4 or CP2 of 1 plus epsilon. Yeah, but then you can rescale everything and you get this famous embedding. But this is only the first new guy of an infinite sequence. It's in the stair business. This embedding here, but there are infinitely many more. These full embeddings at the AN. This one is just the one ball goes to the one ball. This is the ellipsoid 1, 4 goes into the ball of size 2 up to epsilon stretch. One can actually go to the limit and kill the epsilon, but the same method will show all other full embeddings immediately. I will come back to this in tomorrow. One has to rewrite this as a good triangle. But it's SL2Z equivalent, this triangle and this triangle.
Two of the sides are 1/2, right? 1/2, the other is 2.
Yeah, so you see, I started from the convention to embed into CP1, CP2, so that omega evaluated over CP1 is 1. Right, 1, 1, 1. And here the good ellipsoid will be the 1/2, 2. But if you have such a situation, it's very easy to prove that you can always multiply everything. So I can write here lambda and here times lambda, here times lambda. So if I know this, I also know this up to an epsilon. One always has to rescale. So the numbers come in order to distinguish the central tori later, and in order to find these lengths that describe those ellipsoids for which this method gives full volume filling embedding into a ball. You see that some of the little miracle is the old result I proved with McDuff says that on this interval, there are only these points AN where you have full embeddings. But all of these embeddings correspond exactly to all Markov triangles. The Markov triangles give you full embeddings, and they give you exactly those full embeddings that exist, and all other triangles do not fully embed. It's really in bijection. Strangely. That didn't look convincing.
Okay, I think maybe I should listen your recording once again.
Okay, great. And I will prepare a bit more for tomorrow.
Come more prepared tomorrow. Sorry for taking too much of your time.
Okay, no, wonderful. Thanks for asking. So tomorrow I will mostly do this method of displacement energy and use it. So I first come back to the relation Markov triples when one, let's say A is put 1, then you have like pairs, and these gamma n, gn plus 1, these Fibonacci that really establish the staircase. It will just be a repetition and will take 10 minutes, and maybe you can also then ask if there are questions about this first application. And then I show the Vianna tori. So Vianna distinguished them by enumeration of holomorphic disks of Maslov index 2. This is very difficult. It uses neck stretching, and I was not able to follow the proof fully. But with displacement energy, it's totally trivial. Yes.
Okay, thank you very much.
If there are any other questions? If not, let's thank this speaker again.